Okay, so first you need to find eigenvalues, which we're going to look at the determinant of minus lambda I. And then we'll set this determinant to 0 because this is a polynomial. So we set this determinant to 0. Okay, so a minus lambda I means subtract lambda from the diagonals. So then we'll get this negative 2 minus lambda 0, 0. Lambda negative 2, 1, 1, 3 minus lambda. And compute the determinant of this. I'm just going to expand it along the threshold because the threshold has 2 zeros in it. So I take this negative 2 minus lambda times determinant of, delete the first row and the first column, so determinant of this submatrix, which is negative lambda 3 minus 1. And this determinant is so negative 2. So it's going to be negative lambda times 3 minus lambda minus 2, which will turn into positive 2. This is going to be negative 2 negative lambda. This, that's lambda squared 2, 0. And this will be negative 2 negative lambda. And this will be set each one to 0. So this is going to be lambda equal to negative 2. This is lambda equal to 2. So 3 distinct eigenvalues. So that means matrix is diagonalizable. So the answer here is yes. If all of your eigenvalues are distinct, then the matrix is diagonalizable. Then you need to find an invertible matrix P. The factorization exists. And then for each eigenvalue, you're going to find one eigenvector in return. So let me just show you one. So let's say I just started with this. I'm going to start with this one. I call this lambda 1, lambda 2, lambda 3. You can order it differently, but I'm just going to choose this order. So this will be lambda plus 2 identity. This matrix is going to be 2 added to the diagonal. So that's going to be 0 here. 0, 0. 2, 2, negative 2. I'm adding 2 now. So 1, 1. And this will be 5. So now you can just kind of switch this to 1, 1, 5, and put 0, zeros here. You can also make this divide by 2, make this that, and then multiply by negative 1 and add it. So 1, 1, 5, 0, 0, negative 4, and this is 0, 0, 0. So you see this is a pivot position, this is a pivot position, and this is a free variable. So that means you're going to have one eigenvector corresponding to this. So you see, for each eigenvalue, you're going to have exactly one eigenvector corresponding to it. So therefore, you can find a 3 eigenvector and form an invertible matrix P. So then continue from here and find each eigenvalue.